We've already talked about Newton's first and second laws, but there is a third law still to be discussed. And conveniently, that is the topic of this video. So far, we've learned what forces are and what effects they cause, but here we will discover how they are applied, because this is one of the most unintuitive things about mechanics. The thing is, applying a force is never just something that's done from one thing to another, but it's something that happens between them equally. Or in other words, forces are interactions. In his second law, Newton specified what forces are and how they are calculated, the famous F equals ma. Newton's third law describes how they are applied, how they act on objects. Specifically, to every action there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal but opposite. So for each action you will get an equal but opposite reaction. What does it mean? First, a force is not something that an object has, like a property like mass. Rather, it's an action that acts on an object. And actually, this isn't the full story either, because all forces always come in pairs. Whenever I push an object, the object pushes back at me with the same force and the opposite direction. As you might know, it hurts to get punched in the face, but it also hurts your hand to punch somebody else in the face. So sometimes this is really evident, but we might not notice it in some other situations. And I will explain why in some length later. For the moment, let's go deeper into this idea of reciprocity, meaning that whatever happens to one object also happens to the other. This is a more modern notion that describes forces as interactions between two objects. The objects approach, they interact, and they separate again. An interaction is not something one object does to the other, it's something that happens between them and to both of them. And this is a very useful picture of what interactions are and what forces cause, especially later when we get into the other fundamental forces of the Standard Model. At some future time. Alright, I said I'll explain in some length later, so here we are. If you push two fingers together, they will always show the same response. No matter how hard you try, you cannot just push the one into the other, there is always a reaction force back. Because contact is something that happens between two objects and not from one to the other. Talking about contact, the reaction principle actually gives an explanation why all things don't just sit at the core of the Earth. Because if you think about it, gravity is pulling all material objects towards the center of the Earth. So why do they stop on the ground or on the table or on a chair? Because in reaction to the force of gravity pushing down on the table, there is a counterforce pushing back from the table upwards. Where does this force come from? It is a consequence of the molecular forces holding together the components of the table. Now, these will build up as the table is laden and strained, and if they're strong enough, then the table can support the weight and it will hold. Otherwise, it will break. Another insightful example about gravity is this. If forces always cause reaction forces, does that mean that whenever the Earth is pulling you through gravity, are you also pulling back at the Earth? That's exactly what it means, yeah, and with the exact same force too. So why are only you falling towards the Earth while the Earth is standing still? Because, as we learned in the video about dynamics, forces cause accelerations, F equals ma. So the acceleration depends not only on the force, but also on the mass of an object. And everybody already knows that from experience actually. The exact same light push that easily moves a pen does absolutely nothing when applied to your washing machine or fridge. So the pull of gravity, the exact same force, causes a very noticeable acceleration to a human being, but an absolutely insignificant one to the huge mass of the Earth. Technically, the Earth also moves a tiny bit towards you, but it's far too little to be measured. For example, if you go skydiving and you jump from 3,000 meters, which is about 10,000 feet, it will take you about a minute or two to be back on the Earth. It would be about half a minute if all of it were free fall, but let's not go there. And at that same time that you move 3,000 meters towards the Earth moves towards you. But not even by the radius of an atom, but less than the radius of an atom's nucleus. There is often a big misconception about this reaction principle, which can be exemplified by a question. How can a horse pull a cart if all they do is exerting equal but opposite forces on each other? Shouldn't they just stand still? And that's even correct if you really only have a horse and a cart in a vacuum with nothing else around. The horse couldn't move the cart as long as they are connected. If they are not connected, the horse could push off the cart. Or a horse with a cart could push off another cart. On the Earth, the horse has the Earth to push off of, and it takes the cart with it as they are both connected. And actually, this is the exact reason why we can move forward by taking steps. We push back at the Earth, and the Earth pushes us forward in return. There is an additional layer to the reaction law. It was essentially the first conservation law in physics, formulated for the conservation of total momentum of a system. As I said in the dynamics video, the change of motion of an object is proportional to the force impressed, in the direction in which the force is impressed. The change in motion is actually a change in momentum, but for constant mass this is the well-known F equals ma. Newton's laws tell us two things. First, in general, force is a change in momentum. Second, for each force there is always a reaction force that is equal and opposite. In other words, each change of momentum is accompanied by an equal but opposite change in momentum. When each change is countered by an equal but opposite change, in total the net momentum of a system never changes. i.e., total momentum in a closed system is conserved. And actually, because of this, there have been attempts in physics to get rid of the force concept in general and just replace it with momentum exchange. This is also a more modern view that fits better with how interactions are described in quantum theory. However, the force concept was simply too intuitive and familiar for us humans, so it stuck. And this concludes the series about key mechanics. We have gone through all the key concepts of motion and have treated all of Newton's laws now. There is, of course, more to mechanics than this, but this is the hard core. And if you understand the contents of this series, you do understand the most important things about mechanics, the key mechanics.